Hello everyone. We are going to go through for Module 2 the research process. And if you've read your chapters, that's chapters 6 and 7, they talk a little bit about parts of the research process. But since this is actually not a statistics class and in fact is a research methodology class, I thought I would dig a little deeper into the process. We'll sort of cover some of the content that's in chapter 6 and 7, and then I'll throw some other information in and give you a couple of examples. Here is the research process, and this is a little kind of a different view of the research process. The first thing that we do is that in quantitative methodologies is that we'll observe something. We'll observe some phenomenon, something, some process that we're interested in. It could be something like, employees are more productive on the day that they get paid, or people talk more on Tuesdays at lunch, or something like that. Both of those examples are pretty meaningless, but you get the idea that we're looking at some variable that is changing. And not only that, because it's quantitative methodology, some variable that is actually quantifiable. So we'll pull in some data and we'll generate a theory. And the theory is we think that people talk more on Tuesdays at lunch, or we think that there is a likelihood that people are more productive on the days that they get paid. We might even consult the literature and look and see if there's anything that supports that theory that we've come up with. And then if we're truly interested in the theory, we're truly interested in the observations that we're making, we will generate a hypothesis. And the hypothesis is really, this is, when I conduct my research, this is what I believe I'm going to find. Through that process, we'll identify variables, and in generating our hypothesis for a quantitative study, we're looking at variables that are quantitative in nature and ones where we can actually see a relationship between those variables. In some cases, we might actually look for causation, but that's not as common as checking for a relationship. We will then collect data to test our theory or test our hypothesis, and we'll measure our variables, and then we'll analyze the results, and we'll determine the extent to which we are able to support or not support the hypothesis that we are pursuing. So we'll go through a little bit more of each of these steps. So this is the same steps in text. Initial observation is a finding something that needs explaining, and then we'll generate and test theories and hypotheses. We'll collect data for our measurement. We'll collect and analyze the data in our research design, and then finally conduct our analysis to determine whether or not we can actually support or reject our hypothesis. Let's go into it in a little more detail. Actually, I'm going to skip this slide because it's basically saying the same thing that I just said. The first thing we're going to do when we come up with a research design is, in order to be able to support or even make a hypothesis, we have to consider our variables. And our variables are going to be, what is it that we're looking at? Is it variable A is the day of the week, and variable B is employee productivity? So those are two variables. Now, day of the week, that's fairly easy. It's a categorical variable. It's fairly easy to quantify. Productivity, that would have to come up on some sort of scale, some sort of repeating, valid, and reliable scale that would allow us to say this is a true measure of employee productivity. But there could be other variables. There could be time of day and productivity. There could be the score on the graduate records examination, GRE test, and GPA in grad school. Different variables, and it could be multiple variables, not just two. All the examples I've given you just have two variables, but there could be, it could be GRE score, it could be income level, and it could be educational level of the parents as predictor variables for students' GPA, which could be the outcome variable. Okay, so what are we going to examine, and what variables will we use? And that's pretty important for us to decide because it helps us define what our hypothesis is going to be. We will look at relationships between the variables. Now, when you look at variables in a quantitative study, there are two broad categories of variables, and there are multiple sort of subcategories. The first two broad categories are categorical and continuous. A categorical variable is one that has, it's a category. So like I said, days of the week is a categorical variable. It has a fixed number of entries, and they're not numeric, and they are categories. So things that happen on Friday, things that happen on Tuesday. Another one is months of the year. Those are all categorical variables. You can have a categorical variable that is binary in nature, and binary means it's either is or it isn't. It's either yes or no, or it's male or female. It's got two values. You might use those in something like a logistic regression design. A nominal variable is one that is a categorical variable, but there's no order to it. So days of the week might not be a great example because there's a chronological order to that, but you might have, group A, group B, group C. Those are categorical. That's a categorical variable, and there's no real sort of ordered value. Whereas your ordinal variable is a categorical variable, but it is in a certain order: first place, second place, third place. And you might, or group 1, group 2, group 3, if the number on those groups actually has a meaningful use. So those are categorical variables. That's where you're putting people into categories. They're either binary, nominal, or ordinal. The other one is a continuous variable, and these are numeric variables. And these are actually, in quantitative studies, going to be your more common variables. You have an interval variable and a ratio variable. An interval variable could be something like particularly numeric groups that somebody can belong to. It could be something like months of the year, if that could be used as an interval variable, where there really is no starting point, there's no true zero, and they're just categories that your subjects can fit into. Ratio variable is going to be your most common numeric variable, and that is basically numbers. It's values. There is a true zero starting point, and it's just values, and it's measured distance from that true zero. So it can either be a continuous, which is, you can use decimals, that can be positive and negative, or it can be discrete, where you're using whole numbers. All right, let's talk about, once we've selected the type of variables that we want, what variables are doing what? What are the roles of certain variables? So you'll hear the terms independent and dependent variables. An independent variable is one that is not dependent on another variable, hence the name independent. But it also can be one that is used to help define a dependent variable. An independent variable might be, in our earlier example, the day of the week. If we think that employees are more productive on Tuesdays and Thursdays, then our independent variable is going to be the day of the week, because it is what is determining what we're measuring. So it's a variable that we think is a cause, because its value does not depend on other variables. The dependent variable, on the other hand, though, is one that is dependent on one or more independent variables. So it takes its value based on the value of some number of independent variables. Very often it's 1, sometimes it's 1, 2, 3, it could be a number of independent variables. So a dependent variable is a variable that we think is an effect, because the value of this variable depends on the cause. We can also sometimes refer to these as predictor variables and outcome variables. The predictor variable, of course, is the independent variable, because it is predicting the outcome, and the outcome variable would be the dependent variable, because it is what is the result of the relationship. One thing I want you to always remember and never forget: when you're dealing with quantitative methodologies, there are two main types of quantitative methodologies. There's correlational, which is really measuring a relationship between one variable and another, or one variable and several others. And then there is causal, whereas you're saying that one variable is causing the result of another variable. These are not the same thing, and that is one of the biggest mistakes I see in quantitative methodologies, is that students are using what really is a correlational relationship. They're looking at the variables, two variables, and they're looking at the relationship between those two variables, and they're using that in a causal way to try to claim that variable A is causing the outcome of variable B. These are not the same thing. Correlational measures, if there is a relationship between the variables without any concern for cause, that is what we're using correlation for. So determine if there is a relationship, but one variable does not cause the other one. Causal is about cause. One variable is actually causing the other one to change in a clear and predicted manner. Correlation is much easier to defend. It's much easier to set up correlational studies. Causal is much more difficult to defend, and usually requires an experimental design where you have a group that is control and you have a group that is experimental, and you apply, and those two groups are the exact same at the beginning, but you apply some sort of intervention to the experimental group and then measure the difference between the control group and the experimental group. That's a lot to set up, and that's a lot to do. But it can be done. But I've seen many examples, as I said, of correlational research where the researcher is trying to pass off correlation as cause. So don't do that. Here's an example of where you might pass off correlation as cause. So you have 9 subjects, and we're looking at the relationship between annual income and happiness. Now, happiness is some 1 to 10 scale. I just made it up. but let's just assume there's a 1 to 10 scale that's actually valid and reliable and one that we've been able to administer to our subjects. And if you look at it, you've got a really pretty good correlation between annual income and happiness. You have, the lower ends of the annual income have the lower scale of happiness. The upper ends of the annual income have the higher scale of happiness. It is very tempting to say that annual income causes higher happiness. Higher annual income causes higher happiness, but you cannot say that. Not the least of which reason is that you only have 9, an n of 9. That's not going to give you enough data to actually say that. But you also have not set up the experiment to be such that you could actually determine that there is a causal effect here. What you would need to do is you would need to take a group of individuals that were at the lower end of the income, or even all ends of the income, and a group of individuals, and make them your control, and a group of individuals that would be your experimental group. And really you'd have to give them, the experimental group, more money, and then test out whether their happiness went up. That's an impractical and not very sensible experiment to do. But that's what it would take for you to be able to say that annual income caused higher happiness. Right now, the best you can do is run a correlation of this and see if there's a relationship between those two variables and base your research on that relationship, which is perfectly fine to do. If you find that there is a statistically significant relationship between those two variables, there's a lot that can be done with that. But you cannot claim in this design, even with more samples, that annual income causes happiness. Okay. So now we've decided that we've found an observation. We're interested in that observation, and we want to test out that observation. And we've identified our variables. So we're gonna then, as part of the process, we might consult the literature and see if the literature has anything in it about a similar type of experiment or a similar type of comparison. And if not, that's fine. But the literature will be sort of like the overarching kind of this is what's going on in this field, and your observation or your experiment is going to be a subset of that. So we will try to create a hypothesis, and we can go back and use my example here, and we will say that our hypothesis is going to be that annual income is positively correlated to happiness, the happiness score. There's our hypothesis. Okay, so we're going to go ahead and try to test out that hypothesis and see if it works. And we'll be operating under a theory. There could be literature that talks about, relationship between happiness and income. We have stated a hypothesis, which, like I said, is a smaller level of that phenomenon, a smaller level of that theory. And falsification, which you may or may not hear throughout this course, is the failure to prove our hypothesis. It's the failure to get what we thought we were going to get. So just keep that in the back of your mind, is that we may run into that. All right. But now we have to do something else. We have to come up with what's called a null hypothesis. And a null hypothesis is common. It's pretty much required in quantitative methods, because what we want to test out first and foremost is our assumption that there's a relationship. And we do that using a null hypothesis, which states that, in fact, the opposite of what we're looking to find. We're going to state that there's no relationship. So that is our null hypothesis, is that there is no statistically significant relationship between annual income and happiness score. And that will be our null hypothesis. We still have our regular hypothesis that we think that annual income and the happiness score are positively correlated, or they're positively related. So we'll have two hypotheses. The first one is our null. There's no relationship, so that's the null. And the alternative, or the research, the book refers to it as research hypothesis, is that there in fact is a relationship. The hypothesis, the null hypothesis, and the research or alternative hypothesis are really kind of opposites of each other. We state first off that there's no relationship, and then we state that there is a relationship. And whether or not there's a relationship really depends on a couple of different factors. One, is there a relationship that can be statistically shown? And secondly, does it meet our threshold, or does it meet our minimum requirements for us to say that it's statistically significant? So when we run our experiment, one of the things we want to try to do is we want to see if we can reject the null hypothesis. So what are we doing there? Okay, well, we're going to look at our data. First thing we're going to do is analyze our data. So we're going to take our data on annual income and happiness, and we're going to get our results. So we might run a Pearson correlation on this and determine a correlation coefficient, and also get a p-value. A p-value is going to be, and I'll talk about p-value in a minute, but a p-value is going to be a measurement of how confident we are in the results. Okay. So then we ask, we've analyzed our data and we've gotten our results, and we've got a Pearson correlation coefficient. Then we have to ask ourselves, what is the chance I would have found this result if the null hypothesis is true? Okay, so what is the chance that I would have gotten the result if there's no relationship between the two variables? Okay, what is that chance? And there's ways to quantify that, and that's really where p-value comes in. A p-value is really a measure of the chance that you would have gotten your results if there's no relationship between the variables that you're looking at. And that's kind of a key nuance. It's kind of a key specific detail. Because a lot of people think that p-value means something that it doesn't mean. But what it really means is, what is the chance I would have gotten the result I got if the null hypothesis is true? Okay? And it's going to come to some numeric value, probably on a scale of 0 to 100, because it's going to be termed as a percentage. It's a 5% chance, it's a 1% chance, it's a 10% chance. Okay? So in many cases, if there's more than a 5% chance that I could have found this result where there is no relationship between my variables, then I cannot reject the null hypothesis, because I can't say with a reasonable level of confidence that the null hypothesis is wrong. There is no relationship between those two. Okay? But if I get to a point where I say if there is less than a 5% chance that I could have found this result when there is no relationship between the variables, then I can reject the null hypothesis. Now that 5%, that is the most common variable, that's the most common value that we use as a threshold. But it is not fixed in stone, it is not set in stone. And many experiments, when they're getting down, a lot of really defined experiments with large data sets will get down to 1%. So there's a 1% chance. If there's a 1% chance, 1% or higher chance that I could have found my results purely by chance when I cannot reject the null hypothesis, then I have to say that I can't reject the null hypothesis. So I'll talk more about this in a second, but really it's just rejection of the null hypothesis. You state your threshold. In this case, we're going to state the threshold of 5%. If there's a 95%, if I'm 95% confident that I could not have gotten my results if I could not reject the null hypothesis, then I get to reject the null hypothesis. And once I reject the null hypothesis, I'm free to accept the alternative hypothesis. So, and I'll go through this in a little bit more detail. So when I state a null hypothesis, I also state my alternative. So, and they're often designated by H0 and H1 or H2, H3. You can have more than one alternative hypothesis. That H0 is my null hypothesis, and that's the statement of there is no relationship between these two variables. H1 is the alternative, and it's basically the opposite of the null hypothesis. There is a statistically significant relationship, and statistically significant is defined by the threshold I set for my p-value, if it meets my p-value parameters. So when I reject the null, I can accept the alternative. Thus, the alternative should be very tightly tied to the null. You have to have an alternative hypothesis that is related to your null, otherwise your experiment is flawed. The alternative is a statement of the opposite of the null, and the alternative is what I expected to find in the beginning. I expected that annual income and happiness score were going to be positively correlated. So it's what I expected to find. Again, falsification is when I failed to find what I expected to find, because I cannot reject the null hypothesis, so I cannot accept the alternative. Talked a little bit about p-value already. P-value is a probability value. It's the chance that something came about purely by chance. That's often how it's defined. When we test out relationships between two variables, we might get a p-value, or we might get a result where our correlation coefficient is 0.25, but our p-value is 0.001. That is a statistically significant result. The actual measurement of the effect may not be that great because the correlation is only 0.25, but it is statistically significant because it drops below 0.05, which is representative of the 5% threshold that we want to set. In the next bullet point, I state just that. We set a threshold where p is less than or equal to 0.05, or, stated another way, there is a 5% or less chance that the result we got was purely by chance. That's how we use p-value to determine statistical significance. We get our result, we check the p-value. If the p-value drops below whatever stated threshold we have, whether it's 5% or 1%, then we can accept the result as statistically significant. It doesn't mean that it's meaningful. You can have lots of statistically significant results that are absolutely meaningless. In this case, a 0.25 is pretty much getting close to meaningless. It's a moderate relationship. But just because it's statistically significant doesn't mean it's meaningful. If our p-value is lower than our threshold, we can reject the null hypothesis, and that allows us to accept the alternative hypothesis if the alternative hypothesis is stated correctly. There's a less than 5% chance that the result I found could exist if the null hypothesis is true. So that leads me to reject the null hypothesis. Low p-value, reject the null. High p-value, fail to reject the null. Example, I have observed that happiness seems to go up when people make more money. It is an observation that seems to hold true, but is it really true? Is it statistically supportable? So are there any published theories in the literature that support this observation? That would be helpful to find, so I might go look for those. Okay. Then I determine that my variables are annual income and happiness. Great. Annual income is pretty quantitative by itself. It is a continuous variable. Happiness would be a numerical variable, would be a interval variable, actually. Could be categorical, depending on how it's used. My hypotheses. The first one, the null is there is no relationship between annual income and happiness. Okay. My alternative is that there is a relationship between annual income and happiness. And if I wanted to be more specific, I could say there is a positive relationship between annual income and happiness, but I didn't pin it down that tight. So now I'm going to analyze the data. Here's my results. Let's say that I got a correlation coefficient of 0.4, which is a moderate correlation. Moderate, pushing kind of better correlation. Well, my p-value is 0.15. What do? It's not a significant result because my threshold is exceeded. There is a 15% chance that I could have found the results of a 0.4 correlation even if the null hypothesis is true. That's what that 0.15 is telling me. And that's too high. It's too big of a chance to take. I don't want to get false positives, so I'm not going to say that I can reject the null and I have that it's a fail. It's not totally a fail. It does tell me some stuff. It tells me that a 0.4 correlation, I'm not getting a very reliable result. But let's assume for a second that my correlation coefficient is 0.4, but my p-value is less than 0.05. Now that is not too high. It does not exceed my threshold. It does not become too risky that I'm going to get a false positive. So I'm going to go ahead and reject the null. And when I reject the null, I accept the alternative that states that there is a relationship between my variables, because now I know that there's less than a 5% chance that I would have pulled up a 0.4 correlation coefficient if the null hypothesis were true. A very small chance. So I have basically what that translates to is I have a very small chance of a false positive. All right, a couple other terms that the book talks about. Validity and reliability. These two go hand in hand. Validity is basically a tool is measuring what it is intended to measure. And it's amazing how this seems like it's pretty intuitive, but it's amazing how quickly it can go wrong. Especially when you're dealing with surveys and other quantitative tools. They could go astray a little bit and start measuring things that they were never intended to measure. So example could be a survey that asks about customer satisfaction. It cannot be used to measure customer purchasing patterns. Even though you might think intuitively that customer satisfaction would lead to better purchasing patterns, you cannot state that a survey that asks about customer satisfaction is going to really truly return any results about purchasing patterns. Even if they're related, that's not what it was intended for. So that is a tool that is going to suffer from lack of validity. Validity is a necessary but not a sufficient condition of measurement. You need to have a measure, a valid measure, but you also need to have a reliable measure. And the reliable measure, the easiest definition is the ability of a measure to produce the same result when it's used at different times. So it's, you can rely on the result that you're getting if you use it with different groups, if you use the measure with different circumstances or whatever, or if you even actually use it with the same group 2 different times, it's going to return basically the same result. And it's not just a purely by chance or purely kind of luck of the draw that you got the result that you got. I already talked a little bit about this. Correlational research is a natural view of the question, but we're not influencing what happens. It should not be biased by the researcher, but we're really looking at the relationship between 2 variables. And it's kind of just what's there. If you've got a list of numbers and you're comparing it against another list of numbers, and they represent variables, and they're determining that there's a 0.8 correlation with a p-value of 0.001, you've got a good relationship between those numbers. We didn't really have to do anything. We didn't really have to intervene. We just got that result from the research there, the statistics that we did. Experimental research I've talked a little bit about is a much more developed monster. You have dependent variables that depend on the behavior of independent variables. And that's where basically you set up a control, you set up an experiment, at least one experimental condition, if not multiple experimental conditions, and you test out the behavior of the dependent variables under different conditions that are determined by the independent variables. And with all things being equal amongst the groups, the only thing that would be different would be the treatment by the independent variable, and that would be what would be causing any changes you would see in the dependent variable. In experimental design, there are a number of extraneous and confounding variables. Extraneous and confounding variables are conditions in the design that can impact the outcome. They can impact how the independent variable impacts the dependent variable. These can include things like methods of data collection, whether or not we're running between groups or independent designs, or within groups or repeated measure designs. It really is, like I said, it's a much more involved monster. It may make sense for some of you in your research to do an experimental structure. It just depends on what you're doing. But you have to be aware that there are a number of things that can really mess it up. And two things that we'll have to note as we go forward. We want to make sure that we account for systematic variation and unsystematic variation. Systematic variation is basically caused by the experimenter, and it's something that he or she has decided to do in one condition but not the other condition. It's really an experimental design. Systematic variation is the intervention that is done in experimental design that's not done in the control. But it's intentional, and it's something that we have purposefully done. Unsystematic variation can be due to random factors. It can be the time of day, the mood of the day. It could be noise that finds its way in. It could be other factors that will have an impact on the outcome of the study, but they were unintended, but they still need to be accounted for. And then lastly, randomization. When we are selecting groups, if we choose to do things in experimental designs, or even if we don't, other designs can use randomization. We want to make sure that we are careful about how we assign subjects or other things to random groups, because we have to account for things like practice effects and boredom effects. And if we're doing things with a group of individuals and they become aware of what it is that we're asking them to do under some certain conditions, that's a practice effect, because then it's different from when the first time that they encounter the phenomenon. If they're familiar with that and they encounter it again, their results are going to be different. So we have to account for that. And also we have to account for boredom effects. If we have multiple different interventions and we want to subject the same subjects to the different interventions, they could be, by the second intervention or third intervention, they could be like completely over the experiment and done with it and want to get out of there. And that will impact the results as well. So counterbalancing is a process of where we mix up the groups and we set up our experiments and we set up our random distribution so that we can get over or get past things like practice effects and boredom effects. And that's all I wanted to go through this week. If you have any questions, you can always email me. Thanks.